Hello, this is the third part. In the first two parts, we understood the basic separation techniques, and then once we separate the organic compound from its impurities and you get the pure compound, you have to know which kind of elements are present, what are the different elements which are present in that compound, and after that, you need to know the percentage composition. So, we were okay with the qualitative analysis. We have discussed that, right? We understood how do you identify this compound which is a mixture of so many elements, which all elements are present in that given compound. How do you detect nitrogen? How do you understand if carbon is present? Carbon, of course. Hydrogen is present. How do you understand nitrogen, phosphorus? All of that we have done. Now we are doing the quantitative analysis. Quantitative analysis means exact percentage composition of element in that compound, right? In this particular, like for example, if I have to say like hydrogen, for example, we say and per percentage composition, uh, in terms of percentage, what is the percentage of hydrogen here? So there are two, you will say 2 by 18 into 100. The mass of hydrogen present in the compound, and then you divide by the total mass of that particular compound, multiply by 100 to express it as a percentage. Alright, similarly, we also, once we understand that this compound contains these elements, we have to know the percentage composition, and that is what we are going to understand here. Yes. So the first thing here is the estimation of carbon. Okay, so you are going to understand the estimation of carbon and hydrogen, and this technique is what we call as the Liebig's technique, Liebig's method. Alright, yes. So what you do here is I will just draw the rough diagram here. You can just refer your textbook also. You are going to pass dry oxygen here, and here this is what we call as a platinum boat. Okay, because the shape is like a boat. You take a sample organic compound and then you heat it. Alright, and here you have your copper oxide pellets. Okay, this is copper oxide, and then you have your furnace, and here what you have is this is connected to two U-shaped pipes like this. One is this and one is this. Okay, so this is, here you have anhydrous calcium chloride, and here you have KOH solution, potassium hydroxide solution. Okay, let us try to understand this setup. So you take the sample of organic compound. So the sample is weighed. You know the exact weight of it. It is weighed accurately. Whatever it is, 10 grams, 15 grams. Alright, and then it is placed in a porcelain board in the combustion tube. This is what we call as the combustion tube, wherein you can carry out combustion. So the organic sample is placed in the platinum board in the combustion tube, and next to it you have dry cupric oxide, so that there is complete oxidation, and you have two absorption tubes, one which is containing anhydrous, no moisture, anhydrous calcium chloride. Another one contains a concentrated potassium hydroxide solution or ascaride. Okay, these are also weighed. These are also weighed accurately, both of it, along with the tube. Correct? Now, you heat the combustion tube. Since it is oxygen is passed, it is nothing but combustion of the substance. Correct? So, combustion always gives you water and carbon dioxide. The water and carbon dioxide will be passed through the absorption tubes, and then you are weighing it again. The increase in the masses of the absorption tubes gives you the mass of the carbon dioxide and water. Alright, very very simple. So you heat it. So what is the reaction here? I don't know what it is. I'm just writing CHCXHY because you don't know what is the compound, right? The combustion reaction with oxygen. Now this is the general balanced trick to balance your combustion reaction. This is always the general trick. It will always work for sure. You can remember this. It will be helpful. See, if you know it is methane, ethane and all, you can balance it. But in general, this trick will also help you. If you say CX, there are X atoms of carbon and Y atoms of hydrogen. The oxygen will be X plus Y by 4. Carbon dioxide will be X and water will be Y by 2. General reaction. Okay, so combustion will always give you carbon dioxide and water, which will be passing through these tubes. It is already weighed before the reaction and then it is weighed after the reaction. The total weight you will be able to understand. With the total weight, you'll be able to understand what is the mass of the carbon dioxide and water. All right. Now, if you say this weight was x grams, the sample. Okay. Let us say you understood after measuring. Let us say the increase in the weight, that is the mass of carbon dioxide now is a grams, for example. Alright. Now, if you know this, what is the percentage of carbon? Percentage carbon in the compound is given by a formula, which is mass of carbon dioxide. Now, you don't need this A. I'm just going to write you this way. It's very simple. You just have to remember this formula. You'll be getting numericals on this. Okay. So, mass of carbon dioxide form divided by mass of organic compound into 12 by 44 into 100. 12 is the atomic mass of carbon, 44 is the molecular mass of carbon dioxide, right? So, whatever carbon dioxide was formed, you measure it. Mass of the organic compound you already know, 12 by 44 into 100, this will give you the percentage. Similarly, how do you get the this formula? How was it derived? Unitary method. 44 grams gives me contains 12 grams. This much contains how much, and then you are going to convert it into percent. Not required. You can just remember this formula. Percentage of hydrogen will be mass of hydrogen form divided by mass of the organic compound into 2 by 18 into 100. Here also it's the same thing, mass of water by mass. 2 is the mass of atomic mass of hydrogen. 18 is the atomic mass of water, molecular mass of water. That's all. So I'll not be taking up numericals here. They're very simple. I will try to finish all the techniques first, and then if we can discuss the numericals, or you can just go through the numericals. I'm just telling you the technique here. Alright, so this is the first thing. Estimation of carbon and hydrogen is done. Let's go to the second one, that is estimation of nitrogen. So this is nothing but your combustion reaction, but you are going to understand the percentage composition. And based on that, you are going to understand what is that compound. Right? So next is estimation of nitrogen. Now there are two techniques here to estimate nitrogen. First one is the Dumas method and second one is the K-Chedel method. Okay, so there are two techniques. First is Dumas method, which which we'll be discussing initially, and the second one is K-Gildan's method. Right? Yes. So let us understand the Dumas technique first. So what you do here is, here also you have a combustion tube, something like this, okay, where you are going to pass carbon dioxide, right? And then you are taking a known mass of your nitrogenous organic compound in the combustion tube. This is your combustion tube. Okay, so known mass of organic compound. Okay, in the combustion tube you will be taking. And then this also contains copper oxide. Okay, so this also contains copper oxide just like the previous, and additionally it also contains copper gas. This is copper gas. Okay, so what are you going to do? You take a known mass. This is weighed. Okay, some x grams. So you are taking a known mass of the nitrogenous organic compound and you are going to heat it. Okay, you are going to heat it in the combustion tube, and that combustion tube also contains copper oxide. The reason is to remove the atmospheric air. Copper, if there is air, I don't want that air to affect my reading or my calculation. In order to remove air, you are using copper oxide. Alright, and then this organic compound decomposes, it gives nitrogen gas. So what happens? This organic compound decomposes to give nitrogen gas. Along with the nitrogen gas, you are also going to get carbon dioxide, some water and other oxides of nitrogen. Other nitrogen oxides along with nitrogen. Okay. Now the oxides of nitrogen, see this you directly got, but what about this? This oxides of nitrogen are again you have to convert it into nitrogen by passing over the copper gas. That's the reason you have this copper gas. Alright, so this copper gas, from this copper gas you are getting nitrogen, and what happens, how are you collecting it? You are collecting it in this apparatus. Alright, so this gaseous mixture, once you get nitrogen, it is collected over aqueous potassium hydroxide solution. So this is your KOH solution, aqueous. The reason why you have KOH is so that carbon dioxide, it will be absorbed, and nitrogen gas will be collected in the gas tank. So you can, it has got readings, you can measure the reading here. Alright, and from the volume of the nitrogen gas obtained, the percentage of nitrogen can be calculated. So this is connected so that you can understand the pressure. It is connected to a nitrometer, which we also will be dealing with pressure here, so that's the reason. Okay, so this is the setup here. So what is the setup? In order to, we are doing the Dumas method. Okay, this is what we are doing here. So you have a combustion tube where carbon dioxide gas is passed. You have the organic compound which is way before the reactions happens, and you are gonna heat it. Now what happens when you heat it? The organic compound, it decomposes to give you nitrogen because it contains nitrogen, but it does not decomposes to give just nitrogen. You will also have carbon dioxide, you will also have water and other nitrogenous oxides. The nitrogen gas is fine, it will be collected over KOH, but other nitrogen oxides, if you want to convert it to nitrogen, you will be passing it to the copper gas. Okay, so you will be passing it to the copper gas, and then in the KOH you will be collecting the nitrogen gas is collected here. You can measure the volume of the nitrogen. We need the volume of the nitrogen. Okay, so now there is a formula here which you should know. Alright, so yes, so volume of nitrogen gas. I'll just write the formula, then we will write. First, let us consider how to calculate the volume of nitrogen gas at STP. Okay, this is P minus F into V by T into 273 by 760. Okay, so this is the volume. Let me say it is V1 ml. So I am going to calculate the volume of nitrogen at STP. Now what are all this P and other things? Let us understand. P is the pressure of the gas collected. You have connected it to this, so as to measure the pressure of the gas which is collected. Okay. Next, F is the aqueous tension. Because of water vapors, there will be aqueous tension at room temperature, that is F. And then you have V, which is the volume of nitrogen which is formed as per the reading here. Okay, so this is volume of nitrogen. And T is the temperature, room temperature. What else you have? 273, yes, that's all. Okay, so this is the volume of nitrogen at STP, but I don't want that. I want percentage nitrogen, correct? So what will be the percentage nitrogen? Percentage nitrogen present in the composition is X into 100 by small m. What is the small m? Small m is the mass of the organic compound which was initially taken. Okay, this mass which you had weighed here, that is small m. What is this X? I can calculate, where X is equal to 28 into V1 by 2400. It is using the standard principles that at STP, any 1 mole of any gas will occupy 22,400 liters. So you say that 22,400 ml, 22.4 liters, sorry, 22.4 liters of gas or 22,400 ml is 1 mole, that is 28 grams. V1 will occupy how much mass? That is the logic you are doing, and then you are going to percentage divide it, meaning convert it into percentage. So it is X, where X is 28 into V1 divided by 22,400, because our V1 is in ml, so this will also be in ml. And once you get X, you can use X into 100 by m. Alright, now what is this aqueous tension? It is the pressure exerted by the water vapor, and pressure of dry nitrogen is pressure inside minus the aqueous tension. So that's the reason we are going to minus it. The P minus F is actually giving you the pressure of the gas. which included the aqueous tension. That's the reason you're subtracting it. It is basically PV by T only, the same thing. Of course, you don't have gas loss. It is deleted. But if gas loss was there, this would have been easier for you. But anyways, we don't have to really worry about it. For now, you can just remember this formula. 760 is the atmospheric pressure. 273 is the STP temperature. Right, and this X is the mass, the volume at that particular STP, whatever it is. Once you get that volume, you will be able to calculate the percentage nitrogen. That is about the Dumas mass. Alright, so now let us understand kg Dells mass or kg Dells method. So here, what you take is, you take this again we are going to discuss nitrogen only, but using a different technique. So you take a sample of the organic compound the sample is first of all weighed. In all the cases, you have to weigh the sample before using it, before conducting the experiment, and then it is placed in the kg Dahl flask. There is a flask which is called as kg Dahl flask. So this is my kg Dahl flask. And here you are going to keep that organic sample. Okay. Now, you are going to add excess concentrated sulfuric acid. So, you are going to add excess concentrated sulfuric acid, and also you are going to add potassium sulfate to this organic compound. Now, additionally, you are also going to add mercuric sulfate as a catalyst. Okay, you are going to add mercuric sulfate, which will act like a catalyst. Okay, and then you heat the flask. Okay, now once you heat the flask, so let me write it. You heat the flask, and then you heat till the solution becomes clear, and then you cool it. So this is like one step. You are adding this, you are going to heat it, and you are going to cool it. Alright, so after that, what you are going to do is the contents. Now after this step, I'll tell you reaction once, but let us now understand this stepwise. Then I will talk about the reaction in each step, what product is getting formed. Okay, so this contains, once it is cooled, it is transferred into a round bottom flask. Okay, and in that you are taking a strong solution, that is 40% alkali solution like NaOH. Okay, that is what you are going to take, and you arrange the figure, and then you start heating the flask. So basically, what are you going to do? Whatever first set, whatever is the output, you are going to take that content, add it to a round bottom flask, and add 40% sodium hydroxide, and then you heat the flask. What will it give you when you heat it? It will give you ammonia gas that will be liberated, and this ammonia gas will be passed through a condenser, and it is absorbed in a, this is passed through a condenser and absorbed in a known volume of standard acid. Known volume of standard acid, which is taken in your conical flask. So what you do here is, this is after this, okay, after you're heating it, you're getting this, and then you have a conical flask here, and in the conical flask, whatever the contents here, they are made to pass through a condenser. Okay, and then this is connected to a conical flask. Alright, now the unused acid is then titrated against the standard alkali. So whatever is the unused acid, you titrate it, unused acid, you titrate it against the standard alkali. Standard alkali is like, this is 40% or whatever. Alright, so next from this, how do you calculate the percentage nitrogen? Let us understand. Okay, so percentage nitrogen will be equal to volume of acid in ml, which you can measure, unused acid, correct? into normality of the acid. Now what is normality? You do not study normality. Uh, it is another unit, another way to calculate the concentration. You studied molarity, mole fraction, molality and all that. Similarly, we have normality, which will be given to you, multiplied by 14, divided by 14. Why? Because it's the atomic mass of nitrogen, divided by mass of the compound, which was that initially whatever you weighed, into 100 by 1000. Okay, so this formula will give you the percentage nitrogen. Alright, now how do you get this volume of the acid here? Let us try to understand. See, mass you will be given, mass of the organic compound initially you will be calculating. Normality will be given to you. So, normality, even if it is given, you might have to convert it into the normality of the acid will be given to you. Correct? So, very easily you can find. If it is not given, one of them will not be given to you, or they'll give you some other ways to calculate it. Alright, so this is what was originally done. This is what you can measure after titration. Normality in most of the cases will be given to you. Alright, yes. Okay. Yeah, so we had done with the estimation. Okay, let me just summarize this if you want. So what you take, you're taking KGL's in the KGL-DALS method. You are going to take the sample, you're going to weight it, add excess concentrated sulfuric, I have to write the reaction, let me write it. You're going to add excess concentrated sulfuric acid and potassium sulfate and also mercuric sulfate as the catalyst. You heat it till you get a clear solution and then you cool it. Once it is cooled, the contents are transferred to a round bottom flask where you are going to add a known solution of any strong alkali like 40% NaOH. Alright, and then what it gives you ammonia gas which is made to pass through your condenser, and this is absorbed in a known volume of standard acid. Alright, so the unused acid is used to titrate against a standard alkali, and then you can calculate the percentage nitrogen. So what will be the reactions here? Let us write the reactions also. Okay, so first you have the organic compound whose formula I don't know. You are adding H2SO4. The moment you add H2SO4, you are getting ammonium sulfate. Okay, now ammonium sulfate, you add it to, you are passing it over your strong alkali. You will be getting sodium sulfate here plus ammonia plus water. Okay, now let us balance it. This sodium is fine, ammonia will be 2 here, and hydrogen 2 plus 4 8, so it should be 6 here, so 2 here. Okay, next this ammonia gas is made to pass through excess of an acid to give you ammonium sulfate. Correct? So these are the 3 reactions which are involved in this method. Okay, so from that you are going to calculate the your percentage nitrogen. So basically you are going to calculate the volume of an acid into normality into 14, which is the atomic mass, divided by mass of the compound into 10 by 1000. You can write it as 1 by 10, but in case you are wondering why, because this is the conversion into 100 is because you want to express it as a percentage, divided by 1000 is that conversion. Alright, so yes, in the next video we'll be doing the estimation of halogen, sulfur, phosphorus and oxygen.